Okay, I think we're rolling. Just a quick announcement. I did go ahead and upload your exam, your first exam, which is quite a bit late. But anyway, it covers, the material over homework 1 and 2 and kind of where we cut off with lecture around that when those homeworks were released. And so yeah, that's due on Friday. So please be diligently working on that. I've gotten a couple of questions over it, and I had to already found a student had found an error in the exam, and so I corrected that and uploaded it. I also went and graded your quizzes from the various lectures. I caught up with that. And one of the things that I wanted to point out is so when we were talking about super pipelining, for example, students would say, "Oh, the R4000 split up the various caching stages into extra stages, and they did all that, and they super pipelined." Okay, well, that splitting up those extra stages is super pipelining. So I just wanted to point that out. Super pipelining is not something different. It's basically just more aggressive pipelining. And the same mistakes were made with the Pentium, as they said, well, they took two 486 pipelines and put them together so they could fetch multiple instructions, and they implemented superscalar. Well, that is superscalar, is taking those two pipelines and allowing the processor to now fetch multiple instructions per cycle. So anyway, I wanted to point that out. And I don't think there were too many other issues. Most people did get the question I asked about how does the out of order machine maintain precise exceptions, and most people said by committing in order with the use of the reorder buffer, and that's perfect. So I was very pleased with that. Okay, we have more of Chapter 5 material to cover. Hopefully you all are also diligently working on your lab, and that is also due fairly soon. I can't remember when I set that deadline, but anyway. Okay, uh, Chapter 5, where we just started Chapter 5 in the last lecture, and basically what we had pointed out was that over the years, this gap between processor performance and memory has widened quite a bit. And keep in mind that the y-axis in this particular plot here is exponential. Okay, um, it's a log plot, right? Um, so that means that this gap is exponentially widening. Okay. If this was a linear gap, that would still be a problem, but not nearly as much of a problem as we have now. Okay. So just as an example, when we look at 2015, we're basically saying that this gap between processor and memory is 3 orders of magnitude. Okay. From 10 to 10,000. Okay. So 3 orders of magnitude. So how do we fill this gap? Well, what we talked about last time is that we actually fill it with high-speed SRAM that we call cache. Okay. And we keep the cache near the processor small, okay, so it can uh, keep up with the processor. It can run at the speed of the processor. Okay. So if you look at the specs of a new processor, okay, you'll see that the level 1 cache is still about 64 kilobytes. Okay. We're not really seeing level 1 caches go above 64 kilobytes, and we probably never will. I mean, unless we have some game changer other than CMOS that completely changes everything, right? There's always that. But anyway, uh, the level 1 cache is tightly coupled with the processor, and as a result, it needs to be small and fast. Now, as we saw with the R4000, okay, more aggressive instruction level parallelism techniques will actually split up the access to the level 1 into multiple stages. For our simple 5-stage pipeline, there's single cycle access to the level 1. These memories that we talked about in our single cycle processor, when we say, oh, well, we have a separate instruction and separate data memory. Well, those are now caches, okay? So they're actually caches. Those are our level 1 caches, and that's a split cache configuration. And we're going to talk a little bit more about that here in a couple slides. You know, I realized I forgot to add blank sheets to this lecture, so I may have to pause the video and add some blank sheets because I had the urge to draw something, but I can't. Well, actually, I could fit it in here. So, but I will probably pause the video and add blank sheets. So with a split cache, I like to draw it this way. Okay, where this is your microprocessor and this is your instruction cache, and this is your data cache. Okay, we use the little $ symbol for cache, and then this is your next level in the hierarchy. And I don't know why it's not perfectly rectangular shaped. Okay, it kind of dips down here. I'm not sure what feature that is, but okay, so this is your next level, and if you only have one level of cache, so back in the early days, this would be main memory. Okay, so this would be DRAM. Okay, this would be DRAM, and this little level 1 cache here would be SRAM. Okay, and back in the day when we only had one level of cache, our instruction and data caches were only like 4, 8, 16 kilobytes in size. They kind of over the years grew to 64, and then pretty much stayed there. And even application style processors like in your cell phones and everything, as we see in this figure, have 64 kilobytes of level 1 cache. And so we could see throughout the groups of processors, we still have 64 kilobytes. Now, where you might not see 64 kilobytes of cache would be in the embedded world. Okay, so an embedded processor might have a very small cache. Your PIC32 has like a 1 kilobyte cache, but it's very fast in refilling. It can refill a cache line in I think it was 1 or 2 cycles from the internal flash. So you might have sort of novel memory hierarchies when it goes, or maybe not novel per se, but custom memory hierarchies when you go to the embedded world. We found with our crypto code and what we were using our processor for, we could get by very well with a 4 kilobyte cache. And so 4 to 8 is what sometimes you'll see in the embedded world. Okay, but anyway, this is a split cache hierarchy here, and we'll talk more about this later. If you recall, the 486 was unified, which means the instructions and data were stored in the same cache, and it used an instruction buffer to allow instructions to be buffered up when the data side is not accessing the cache. Okay, so that was how they resolved that structural hazard. And one of the things the 486 paper said was that, you know, in fact, oh gosh, I should pull that up. Yeah, let me pull that up because that was a really interesting point. One of the things they said was that that with the unified cache, one of the advantages of a unified cache is that let's see, I store this in my 438. Let's see. Let me go ahead and open both of these in case I need to reference them in this discussion. It didn't give me an open with option, but I think it usually opens with this by default. Okay, so it has not loaded the 486. Okay, thank you. Appreciate you doing that for me. All right, let's see. Okay. One of the things they talked about in the 486, okay, was the fact that the unified cache, one of its advantages is that it adjusts, okay, its capacity between instruction and data according to program heuristics, or really the program operation. Okay, so that is one of the advantages of a unified cache. So what we see here with this paper is, let's zoom into this somewhat unreadable diagram. All of this here, all of this space here, okay, in this shaded, this pattern shade, this is all code. Okay, so those are instructions. Okay, and these are lines. These are your lines of cache that go up to 512. Okay, so here we can see that 300, over 300 lines of our cache are dedicated to code. Okay, and then here we see about 100 is dedicated to, with this squared pattern here. Here is dedicated to read-write data, and then about 50 or so lines is dedicated to read-only data, which is right here with this pattern here. Okay, so this is one particular application, and this is over time how it changes. And the other thing, I mean, just look how it changes over time. Okay, so at this point in time, there's a lot of read-only data in the cache and less instructions. Okay, and just changing applications, here we see mostly read-only data. It's all of this. All of this is read-only data, and very little of the cache is filled with code. Okay, and here we see wild changes over time as the application runs. Okay, where it starts off over here where it's mostly code, a little bit of read-write data, and a lot of read-only data. So that's probably start initialization of a program. And then as time goes on, the read-only data for some reason starts to dominate, and then and it wildly varies. So we see that the amount of necessary instruction cache versus data cache wildly changes. Okay, as time progresses, and from application to application. So within one application, as time progresses, the needs of a program change, the caching needs of a program change, and then application to application has different needs. Now, these were smaller caches. Okay, so 512 lines of caches, cache lines. So I forget what size. I think it was an 8 kilobyte cache, if I remember right. Let's see here. Let's go look. Yeah, 8 kilobytes. So with an 8 kilobyte unified cache, the advantage you have with the unified cache is it can adjust to the needs of the application. Okay, but 8 kilobytes is pretty small by today's standards. So what the Pentium did is the Pentium went with a split cache, and one of the reasons they went with a split cache, which is not really that we didn't really discuss it the last time, is now you have two pipelines, which means you have potentially each pipeline could be trying to access data at the same time. So the structural hazard is exacerbated, right? So now you have two data ports and a single instruction port, because it still fetches when it fetches on the front end, it still fetches like a 16 byte chunk of data, and then decodes that and then splits it down. So you're still fetching once, even though you're gonna pull two instructions from that buffer, but you're still fetching once. So you have one giant fetch that you do for instructions, and remember with a 486 we had said in the pipeline that you actually don't do the fetch on every cycle, because you pull 16 bytes and you basically chew on that and pull instructions from it, and then once you're done pulling instructions from it, or you encounter a jump, then you pull a new 16 byte chunk. Okay, and so the Pentium does that, even though they went superscalar. But now what you have is you have these two pipelines that could be reading data. So now you have even a structural hazard amongst the data cache. So this necessitated them to split the caches. Okay, so they had to have the separate instruction cache and data cache because the structural hazards just got too large. And then they have to have this dual ported data cache to deal with the structural hazards between the two pipelines. And interestingly enough, this is what we do in a small embedded system. Like when we implement our processor on an FPGA without a cache, this is how we resolve that structural hazard between the instruction port and the data port. Is we use dual port RAM. Dual port RAM is natively built into FPGAs, so it works great. And so we'll have one port for instructions and one port for data. Well, what they're doing in this case is they're using one port for the U pipeline and one port for the V pipeline. That's what they called the two separate pipelines. Okay. Well, I'll continue to return to these papers and then also the R4000 papers we go through chapter 5 because a lot of the engineering that went on between these three designs was in the memory hierarchy. We already talked about the designs that they made in terms of pipelining, okay, and so chapter 4 material. Okay, all right, I'm really getting ahead of myself. I'm really off track. I apologize for that. Okay, so that was more than what we talked about last time, but okay, let's continue looking at how this works. Okay. All right. So how does caching even work? How can we use these smaller SRAMs to cache our data and actually achieve decent performance? And the answer comes down to the principle of locality. Okay. There's two types of locality. There's temporal locality and there's spatial locality. Temporal locality says, you know what? If you use a piece of data, there's a high likelihood you'll use it in the near future. Okay? And so that's temporal locality. Spatial locality says, you know, if you use a piece of data, there's a really good chance that you're going to use its neighboring data as well. Okay? So programs exhibit high amounts of spatial and temporal locality. With spatial and temporal locality, it means that it's useful for us to cache the data. So when we pull data in, there's a high chance we're going to reuse that data, which is your temporal locality, because of temporal locality. Okay? And likewise, when we pull in one piece of data, let's not just pull in that one piece of data. Let's go ahead and pull in its neighbors as well. And that allows us to exploit spatial locality. Okay? And we know that programs exhibit a lot of spatial and temporal locality, and we'll talk about why. Okay, think about the way we fetch instructions sequentially. That just naturally breeds spatial locality, right? We know that if we use one, if we fetch one instruction, there's a high likelihood we're going to fetch the next instruction. Okay, so when we encounter a piece of data that's not in the cache, we're going to go ahead and bring in that data along with its nearest neighbors. Okay, and the other thing is in terms of temporal locality, we have loops in our program. So we have branches and jumps that then jump back to where we were before. So that means there's a high likelihood that we're going to reuse those instructions, right? And the same goes for data. Okay, we tend to store data in arrays, which are sequentially located chunks of data, right? So that is how we have spatial locality on the data side of things. And then of course our loops, cause us to churn over the same data. If you think about like matrix multiply, right? You have what is it? It's like doubly nested loops, right? Acting on that data, okay, on your matrices. So if you can think of matrix multiplication, it's like the quintessential high performance example for parallel computing and instruction level parallelism and all that. And so the data within the matrix are continually being processed, right? So there's lots of spatial and temporal locality. Matrix multiply is a very cache-friendly operation. Okay, and that's another thing. When I say a program is cache-friendly, I mean that it exhibits large amounts of spatial and temporal locality. I probably already used that term when we've been looking at different benchmarks, and I say, oh yeah, this is a very cache-friendly benchmark, like your matrix multiply. Okay, not so cache-friendly benchmarks are like streaming and multimedia, where you're from the data side, they're not very cache friendly because you're bringing in data, you're doing an operation on it, and then you write it back out, and then you never touch it again, right? Now it does exhibit lots of spatial locality, but it's not good for temporal locality, and so as a result, it may not be all that cache friendly. Okay. All right. Let's see. Okay. How does the cache exploit this temporal locality? Well, again, this is just a little bit of a review. The cache is a smaller SRAM that keeps recently used data. You're going to see we use this term quite a bit for like a cache replacement policy and everything. Least recently used data means that data has a less likelihood of being reused than most recently used data because of temporal locality. Okay. Access to this cache is fast because it's small, so again it keeps up with the speed of the processor. Okay, and data is transferred between the cache and the next level in the hierarchy. Okay, so when you access the level 1 cache, if the data is not in the level 1 cache, then it goes to the next level up and pulls data from that. Okay. Now, it pulls data from the next level in blocks. Okay. I use the term blocks, and so cache blocks and cache lines synonymously, and you'll see them used differently. In different literature, you'll see them used as describing the same thing. So a cache block is a cache line. Okay. And what it is it's a grouping of data, of words. Okay. And that's the size of data that's transferred between the cache and the next level up. Okay, so we'll see some diagrams here later that describe that. Okay, so that's where we exploit spatial locality. Okay, by pulling in data at this block granularity. Okay, so multiple words. So when we have to go retrieve data from the next level, we don't just get the immediate data that the processor is requesting. We get a block of data which that data the processor is requesting is part of. Okay. Okay. That also, by grabbing data in blocks from the next level, allows us to take advantage of bandwidth. Real quickly, one thing I wanted to remind you about is when we talk about memory performance in this particular graph, we're actually talking about latency. And remember, in chapter 1, we talked about the difference between latency and bandwidth. Okay, and they're two different things. Just like when we talked about pipelining, we saw that pipelining increased the latency of instruction processing, but it improved the bandwidth. Okay, so with memory, the latency hasn't improved all that drastically, but we have done a lot of things to improve the bandwidth. Bandwidth is actually an easier thing to improve than latency. For example, in terms of DRAM, we just increase the number of DRAM chips that we access in parallel and increase the amount of wires between our DIMM, dual inline module, and our processor. Okay. Now, of course, I say we just do that, but I/O pins are a precious resource, so we can't always do that easily. But also with the DRAM, we pipeline it, right? So pipelining allows us to improve the bandwidth. Okay. And so again, we want we want our memory hierarchy to take advantage of that bandwidth that we have at the next level. Okay, so that's important. Okay, let's see. I think it's time for a lecture quiz. I'm going to try to remember to do these. I want you to define temporal locality and spatial locality. Those are two separate things. So I want you to provide the definition for temporal locality and provide the definition for spatial locality. I'm going to go ahead and make sure this video is recording and add a couple of blank sheets here in the lecture. All right, back again. So, well, the video has been recording, so I think hopefully my technical difficulties are over with this new version of Active Presenter. All right, so where we left off was we were talking about how we use these smaller SRAMs to exploit locality, temporal and spatial locality in our programs. So these small memories cache our much larger memory. And again, remember the whole goal is we're trying to create this illusion to programmers that they have very large and very fast memory, because that's what they demand. Larger memories and faster processing power, which equate to faster memories. So we get the fast response from the memories, reduced latency from these smaller caches, and we get the large capacity from the DRAM. Okay, and the hardware is continually transferring data between those memories. Okay, and that's when we say the cache is hardware managed, that's what we mean, is that the hardware is managing the transfer of that data. It happens unbeknownst to the programmer. And in fact, so interestingly enough, when x86 was developed, you started with the 8086 and so on and so forth, all the way up to, well, I don't know, they stopped using the number conventions. Then they just call it x86. But anyway, when that ISA was developed, caches weren't even a thing, okay? And so the 8086, for example, did not have cache, okay? We started seeing caches being introduced in the 386 and 486, okay? The 386 had an off-chip cache, the option for an off-chip cache, and the 486, of course, its big improvement over the 386 was an on-chip cache. And so... So as a result, because the ISA didn't have this concept of caching built into it, then everything has to be completely hardware managed. Okay. Now RISC took a little different approach. Of course, remember the whole goal with RISC is to reduce the hardware footprint to allow us to put more powerful microprocessors on a single die, right? And so we want to reduce the hardware complexity. And at the time, caches were becoming more and more of a thing, and so having a larger program space as a trade-off for performance was a good one to make. So the RISC approach is that the operating system is aware of the cache, and the operating system will have to do odds and ends to clean up weird behaviors that we get with caching, which I'll describe those as we move forward in Chapter 5. One of them, for example, is memory consistency between the instruction and data cache. Okay, when you load a program or modify program space, that modification, it's kind of almost like self-modifying code. When that modification is made, it's made through the data port. But then, well, now the instruction cache has to be flushed in order to keep those two consistent. We'll talk more about that as time goes on. But anyway, those little things, and also invalidating cache lines and setting up the cache and all of that. In a RISC machine, there are special privileged instructions that do all of that for you. Okay, and so whereas in the x86, like for example the 486 and Pentium, all of that stuff has to be done in hardware. So the x86 architecture has always taken has always been on one opposite end of the spectrum, and that's completely hardware managed, where not even the operating system has to be aware of the cache. Okay, and then on the complete opposite end of the spectrum is what we call scratchpad memory or a software managed cache. And actually, an example architecture that you all might be familiar with, or at least you'll be familiar with the application, is the PS3. The PS3 had what was called a cell processor or cell architecture, and it had one main core and then these 8 little helper cores. And then communication between all the helper cores were with these software managed caches. So as a result, the programming for the cell processor was a bit cumbersome. I actually had the opportunity to meet the lead architect for the cell processor, Peter Hofstees, and he from IBM, a very down to earth guy and very intelligent. The the thing is the reason that cell architecture didn't do so well and was later replaced with an Intel product was mainly just because of the difficulty in programming. The architecture itself uh, was very efficient, and programmers that could program for the cell architecture, could make that thing run circles around its competitors. But the fact is that it required intricate knowledge of the memory hierarchy underneath, and and as a result, it had less abstractions to make the programmer's life easier. And so then it was replaced with an architecture on the opposite end of the spectrum when it comes to memory hierarchy, where uh, an Intel processor, where the caches are completely hardware managed, and the programmers enjoyed that a lot more. Uh, but you could still get a cell processor to keep up in terms of performance with a fairly new Intel processor, just because of those software managed caches. Okay, and so then RISC is a point in between that completely software managed cache and a completely hardware managed cache. The operating system for a RISC processor has to do certain things to maintain the cache, and we'll talk about those as time goes on. Okay, all right. So again, all of that's managed uh, in the hardware. And so this is what it looks like. Here's a very simplified diagram of how we're actually transferring data between the processor and this intermediate uh, cache. And this could be level 1 and then level 2, or if it doesn't have a level 2 cache, okay, this could be memory, okay, or it may even extend beyond that and have a level 3 below that. Okay, so that has 3 levels of cache. Uh, so anyway, that's really how this data transfer works between the processor. We can see that this particular block right here is actually also stored here, and that's assuming an inclusive cache, and we'll talk about what that means in a bit. Okay. Okay. So the processor directly accesses the level 1 cache. That's what we see. We don't see the processor jumping over here. That path doesn't exist. Okay. Now, if this was main memory, then there would be a special path that allows the processor to directly access main memory uncached um, for certain corner case situations, or like memory mapped I/O. You don't cache memory mapped I/O. The processor directly writes to the peripherals um, through that memory map. But so that those I/O devices live in the section of uncached kernel space. Okay. After we get done with all of this caching and everything discussion, and once we talk about virtual memory, we'll talk about the typical memory layout of a Linux system. When we'll show you the where user space is, and then I'll show you where kernel space is, and then within kernel space I'll show the break up of the various regions. In kernel space you have unmapped, uncached, you have cached but mapped, and so on and so forth. And then of course you have mapped and cached, and we'll talk about what all that means once we cover virtual memory. But at this point, we don't quite have enough information to understand that. Okay. All right. So, all right, we got a little bit of terminology here. So again, the processor directly accesses the level 1 cache if the data that the processor is requesting is in the level 1 cache. Okay, then a cache hit happens. Okay, and the cache just directly delivers that data to the processor. That's the fast case. And if it's a well-designed memory hierarchy, that's the common case. It's common that the data that the processor is requesting will be in that level 1 cache. Okay, even though it can be relatively small compared to main memory. Okay, if the data is not in the level 1, then what happens is what we call a cache miss. Okay, and so in that case, the processor has to wait for the data, and the level 1 cache says, "Hold on, I don't have it, and so I'm going to go get it." And so then the level 1 cache then retrieves it from the next level in memory. And again, if the design only has a single level of cache, then it retrieves it from main memory. Okay, so then it'll go through the DRAM controller and access it through DRAM. DRAM is so complicated it has to have its own controller. So when you look at a die shot, where they break the die up into different parts, you'll see the processor, the different levels of cache, and then you'll see usually on the perimeter of the chip you'll see a DRAM controller, and of course that's because it's very I/O intensive to communicate with external DRAM. But the DRAM controllers are actually located on the perimeter of the chip, and I use the plural form DRAM controllers, and that's because high performance processors will have multiple DRAM controllers. Okay, because you'll have multiple processors requesting data from DRAM at simultaneously. Okay, so we're introducing some new terminology here. Okay, and so that's cache hit and cache miss. So because we have a cache hit and a cache miss, we also have this metric of hit rate and miss rate. Okay, so the hit rate is nothing more than the ratio of cache hits to the number of accesses to the cache. So if 9 out of 10 times the data that you're requesting is in the level 1 cache, then you have a 90% hit rate. Okay, the miss rate is just the mirror of that, and so if in that example the miss rate would be 1 out of 10 or 10%. Okay, so so it's the ratio of the cache misses to the number of accesses to the cache. These are important metrics, and we're going to talk quite a bit about hit rate and miss rate as time goes on. And of course, our goal is to design a well-designed memory hierarchy, reduces the miss rate. Now, there's another concept called a miss penalty, and we'll talk about that. And so it's always a balancing act between miss rate and miss penalty. Okay. All right. Extending to multiple levels is very easy, and notice the way when I've been talking about this, I've been talking about it in terms of either a single level or multiple levels. Okay, so in the early 80s, level 1 caches were really all you had, and they were starting in the 80s. They were starting to be moved on chip, and that was huge. When the 486 was published, a lot of the RISC processors actually had off-chip level 1 caches. Okay, and if you read the 486 paper, they talk about one of the advantages of going with a unified cache versus a split cache is they could fit the entire cache on chip, and that provided significant performance benefits. Okay, and so that's where the unified cache won out over the split cache design in the architect's minds for the 486 is they could fit it on chip, whereas compared to previous or current RISC designs of that time, they required the split cache because of the five-stage pipeline design that we've talked about quite a bit, where the instruction memory and data memory are separate, and so that meant that those caches had to be off chip because they couldn't fit them all on chip. So now, of course, as time progressed and they were able to fit the level 1 caches on chip, then and they could fit large enough on chip caches, so they could dedicate, for example, 8 kilobytes to both the instruction cache and the data cache. So the iCache and data cache are each 8 kilobytes in size, and then they're split. And so that's where the Pentium came in. Is Pentium was fabricated with a newer process technology, and at that point they went split. And of course, remember they also went split because they also went superscalar, and they had to then resolve the structural hazards between the two pipelines, the U and V pipeline. But the point is that at that time they were able to fit now two separate caches on chip. Okay, and that was huge. And that of course the Pentium was released in '93. By that time, RISC processors had also started fitting their caches on chip. Okay, and now at the time, the Pentium actually supported a off-chip level 2 cache, and I even remember that playing around with, in the late '90s, I would play around with what was considered antiquated hardware, which was developed in the early '90s, and I remember, we actually got our school got a bunch of computers donated to them from Sandia Labs, and of course, Sandia Labs has money to buy the latest and greatest, and so one of the motherboards that I was playing around with had an off-chip level 2 cache, and the Pentium supported that. So in the early '90s, we were starting to see level 2 caches becoming more of a reality, and they started off chip. And then eventually we were able to move them on chip as we continued to progress in our semiconductor fabrication techniques. We moved to smaller and smaller feature sizes, and so the way we actually filled that is we just started putting more and more things on chip. And now we're in this era of system on a chip where you could buy a low-end application performance processor that you might put in, for example, a home network router or something of that nature that has on-chip level 1 and level 2 caches. Okay, and even some of the higher-end application processors can have on-chip level 3 caches. Okay, and that's for the embedded market, mind you. And of course, when we're talking about the mobile market, your mobile phones, they have on-chip level 3 cache. Okay. So anyway, again, we could just continue to extend this memory hierarchy to more and more levels. Okay, and this cutesy little diagram kind of shows how the size and speed of the caches change as you move down in this hierarchy. So as you move away from the processor, okay, which the processor's up here, as you move away from it, the caches get larger, okay, which is what we see here, and they get slower as we move down here. As you recall, larger memory equals longer access time. Okay, there's just no way of getting around that. Okay, and then of course your last level in the hierarchy is generally your main memory, and that is oftentimes off-chip DRAM. Okay, now we are starting to play around with these different 3D and 2.5D packaging, where we're actually packaging DRAM in the same package, but still on a separate die as the processor, and of course that decreases the interconnection lengths, wire lengths between the processor and the DRAM, which increases the speed, and it allows our DRAM to run even that much faster. Okay, And also I think there are technologies that have the DRAM integrated on the chip, so we're actually moving on in certain applications we actually can move the DRAM on chip. 3D technology is where we stack the dies on top of each other, okay, and 2.5D is where it's kind of the half D is saying, hey, it's an intermediate step between 2D, which is where we've been at for years, and 3D, where you're stacking dies, where we have an interposer board, and we put the dies next to each other, okay, and then we package those dies over the interposer board. The thing about it is, if you actually delaminate a microprocessor, you're going to find that the die is still very small compared to the overall packaging. Okay, because you're limited by the pitch of your ball grid array that is used to solder the chip, what we call the chip, onto the circuit board. Well, the actual die, is much smaller than that BGA package. So we can actually fit multiple dies within a package fairly easily. Okay, but there's yield problems. It's a tricky manufacturing problem for the folks that package. You can end up having cracked dies and all kinds of weird things like that because you have different coefficients, thermal coefficients of expansion and all of that. It becomes a material science problem very quickly. Anyway, so again, your last level is typically DRAM, and that's just because of its density. Okay, but you could be building a custom microprocessor system where your last level memory is actually SRAM. Okay, and like the PIC32, that's well, the PIC32, the last level is flash. Okay, and so it caches out of flash. Okay. Okay, yeah. So we got a blank sheet here because I wanted to actually do a little drawing. So let's again, I'm going to draw this as a split cache design. So you're gonna start getting tired of these diagrams. Okay. So this is your I cache, and then this is your D cache, and what they do is they access this, let's say the level 2, and then we generally have a bus between these different uh, devices. So we can have these different buses. So in this case, when we talk about buses, we use the master-slave terminology. So the I cache and the D cache would be the data cache, instruction cache and data cache would be masters on this bus, and then the slave would be the level 2. So what this does is this allows both the instruction cache and the data cache to access the data on the level 2, and then the level 2 is unified. Okay. I have not really seen a split level 2. It just doesn't make any sense. The level 2, remember, is on the order of 256 kilobytes on a high performance uh, or even a lower performance application uh, architecture. And I always talk about application processors. Application processors like the ARM A series of processor, A being for application, uh, they they're very general purpose, and so they have what's considered a very typical memory hierarchy, like we saw in that diagram. Let's just jump to it, like we talked about here. This guy. Okay, these are all application grade, but of course they move to higher performance as we move down. From A is kind of your mobile device. Okay, also, you like a networked router or whatever like that. That's what the A series are used for. Now, ARM also has an M series, which is their microcontroller base, which those are your embedded ones, and those do not follow a typical memory hierarchy. Okay, so that's why I really don't use them as too much of an example in this chapter, although I will provide little anecdotes about how they do things differently. Like I mentioned, in a microcontroller, your last level memory may actually be a flash device, flash memory, okay, which is pretty slow, okay. But microcontrollers are slow anyway, and so with the cache, it helps where you can actually execute out of the flash device, okay. Okay, and then in this case, I'm going to say on the order of 64 kilobytes here. Both are. level 1. So when we have a split cache in the application realm, we have about 64 kilobytes for both the instruction and data cache. And again, in the embedded world, these could be well, actually, the PIC32 has a 1 kilobyte instruction cache, and it doesn't even have a data cache. Okay, so 1 kilobyte all the way up to 8, 16 kilobytes. It's pretty typical for an embedded platform. Okay, so anyway, this is where we go from from split to unified. Okay, and this is referred to as a modified Harvard architecture. Okay. Oh, my spelling is terrible. Okay. I'm not sure if I spelled Harvard right. That's why I didn't go to Harvard. Okay, my GRE scores were so bad on the literature part that the department head where I was getting my master's asked if I spoke any other languages. That's always been my weak point. A lot of engineers are that way. But anyway, and this is a great quiz question. So this is your second quiz question. Define a modified Harvard architecture. Okay, so the modified Harvard architecture is where we go from a split cache at the level 1 to a unified cache at the next level. And and contrast that with a complete Harvard architecture where the hardware is where you at the programmer level you actually do split your instructions and data into separate memories. Okay, and on the other end of the spectrum is von Neumann where instructions and data are stored in the same memory. So what the modified Harvard architecture allows us to do is have our cake and eat it too, so to speak. So at the hardware level, we can have a Harvard architecture, which allows us to split those instruction and data cache separately, the instruction memory and data memory separately, like we talked about all through chapter 4. But then at the programmer level, we unify it. So at the next level, okay, whether that be level 2 or main memory, okay, we then unify the caches, and so now the level 2, for example, in this example, okay, stores both instruction and data, and it could do so because it's much larger than the level 1. Okay, and so then at the programmer level, it's a von Neumann architecture, but under the hood, it's a Harvard architecture. So that's a modified Harvard architecture. Okay, all right, continuing on. So we were talking about extending this to more levels. Well, now we can extend this to a level 3. Okay, so we can put a level 3 here. And whoops, that's supposed to be a 3. So and the concepts we talk about with cache hits, cache misses, fetching data, all of that applies here. Okay, so now the level 2 fetches from the level 3. Now actually, what I need to do is I need to draw a bus in here, and there's a bus here, and this particular level 2 is a master, and then the level 3 is a slave on this bus. And then what's interesting is this is where we get, I don't have enough space here. If I had a longer whiteboard, I would duplicate this processor drawing that I have here and connect it up to the bus, because that's now how we support multiple processors. Okay, so for example, at the level 3 level is where the processors then share memory. So then each processor typically will have its own private level 1 and level 2 caches, and then they'll share the level 3. Okay, so just imagine in this diagram that I duplicate this processor and level 2 diagram and connect it up to this level 3 bus here. Okay, and so then that allows us to share memory. Okay, so memory is shared at the level 3 typically. Okay. All right. And later in chapter 5, we're going to go over how that memory sharing happens, and it's with what's called a cache coherency scheme. Coherency refers to keeping the private caches amongst all the processors consistent and where they have the same data when they're sharing memory. Okay, and then there's it's a little tricky, and there's some inefficiencies that go along with that as well. You may not go out and design processors after taking this class or my 538 class, but what you will get from it is an understanding of how things, a better understanding of how things operate under the hood. And so, for example, programmers that are programming for the cell processor could certainly use this information to better program for that processor. And the reason that most programmers don't do well with a complicated high performance architecture like the cell processor because they don't want to know these things under the hood. But you will be, if you go on to be a programmer, you will be a much better programmer by knowing these things that go on under the hood. Okay? Just like race car drivers are better drivers by knowing how things work under the hood. Okay? All right, so let's just review memory technology. So the SRAM is used for level 1 through level 3. Okay, because it's fast. Okay, now it's not very dense. It's not as efficient in terms of density, so it takes up more chip space. Okay, than DRAM. And DRAM is used for level 4 and main memory. Whoa, now. So now I'm telling you that there's a level 4, and that is the case. We're starting to see level 4 caches, and level 4 caches are typically made out of DRAM that's used in a die stacking configuration. So either 2.5D integration or 3D integration. And so what they'll do is they'll take that extra extra DRAM die and package it with your processor die. And so the level 4 is actually used a lot of times for sharing memory between uh, between GPUs and processors. Okay, so it's a little bit higher performance there. Okay, also you could have multiple processor dies and they share at the level 4 level. Okay, and so that's starting to become a thing. And then of course DRAM's used for main memory, and the reason is because of its density and its cost. Okay, it's a lot cheaper than SRAM. And so when you have to pay the penalty to go off chip, you generally go DRAM. Okay, so that's kind of the way I always think about it. Is all most on-chip memory is SRAM, and off-chip memory is mostly DRAM. And I mean, like we use these. My team uses these little evaluation boards that you could buy for a couple $100 that have a 256 uh, uh, megabyte DRAM chip that the FPGA can access. So DRAM's very prevalent. Okay, and then of course flash and magnetic disk are used for the file system. Okay, for storage. And that's because they're non-volatile and extremely dense. They're even more dense than DRAM. And the key there is, of course, they're non-volatile, which, what that means is that when power is removed, they retain their memory. And so, whereas DRAM and SRAM, when you remove power, they lose their memory. And so, of course, that's where you generally store your operating system, your application code, and all of your user files, right? So now the file system is all managed by the operating system. So I'm going to draw a line here, and I'm going to say OS managed, okay? Managed, and I spelled managed wrong. Managed. It's always embarrassing spelling in front of you guys. Okay. So that's operating system managed, and then generally all of this is hardware managed. Okay. Uh, and and so I don't. If you're dealing with an embedded system, you might be using flash as your main memory, and that's still hardware managed, but that's a unique special case. Okay. Access time, we see orders of magnitude difference between these different access times. And so for example, the level 1 cache probably has an access time closer to a half a nanosecond. Okay, if you're running your processor at your simple 5-stage pipeline processor at 2 gigahertz, okay, you would need about a half a nanosecond of access time for DRAM. So I'm sorry, for your SRAM, your level 1, the uh, instruction cache and data cache both would have to run at a half a nanosecond or faster. Okay. Now, if you want a larger level 1 cache, okay, then you're going to have to pipeline it, and that's where you start getting into your super pipelining, which would be like your 8-stage RISC processor, like the R4000, where they went ahead and split the instruction and data caches up into two stages. Actually, technically, it's 3 stages. We'll talk about that when we talk about the R4000 more. It actually split the instruction and data cache up into 3 stages. We have to understand a little bit more about caching to understand how they did that. The actual data store is split into 2. Okay. Now, then as you move up in the hierarchy or down, depending on how you visualize it, as you move away from the processor, then your SRAM becomes larger, and so when you're in the 256 kilobyte for level 1, you're closer to 2.5 nanoseconds of access time. Okay, level 1 and level 2 is going to be on the larger end of the access time. Okay, and then two orders of magnitude higher, we have DRAM. Okay, and there's not a huge variation between the DRAM. What we do with, because we employ banking techniques in DRAM, and we'll talk about what banking is, but it allows us to expand the size of our DRAM without really increasing the access time. Okay, and then like 2 more orders of magnitude higher, we have flash. Okay, and then 3 orders of magnitude higher, we have magnetic disk. Okay, in terms of access time. So again, these are OS managed, okay, and this is hardware managed. Okay. So for the operating system, your magnetic disk access is in the milliseconds of time, which isn't all that much actually at the operating system level, and so a few milliseconds to access a file is not bad. Okay. Not even we don't as humans, we don't even perceive it. So having this slow storage, much slower storage for our non-volatile storage for our file system works out quite well. Okay, and of course there's even caching that goes on inside the hard drive and whatnot. Okay, whoops, I dropped my digitized pen here. I have to crawl under the desk to get it. Okay, all right. All right, I have a little space here because I just wanted to remind ourselves of what these different cells look like, just so we can kind of put it all together. So this is our SRAM. Okay, so it's a cross-coupling inverters, and then we have these pascades. Okay, and they connect to the bit lines, and we have B and B complement. And then the gate of our pass transistor is connected to this word line. I should have put a couple of these pages in because I'm going to quickly run out of space. And then, of course, remember we have the column, or the row decoder is what actually lights up these word lines, because remember, we're going to have multiple word lines as we go down. Okay, and then and that's the first part of the address. The address into our SRAM is broken up into 2 parts. The word address and the column address. And so the word address is the first part, and well, actually, if you look at it in terms of the address, it's the most significant bits of the address are the word line. And then the least significant bits of the address are then used. If you can imagine, if I had a bigger whiteboard, you would have. I guess I could just draw it here. You would have each of these bit lines, and they, of course, they go into a sense amp, a differential sense amp, and then I'm just going to draw it off to the side here. If you can imagine each of these outputs of these sense amps go into a multiplexer. Okay, and of course we group the we might group 32 bits together. Okay, and each of these is 32 bits, and then this is your column address is the select line on the multiplexer here. I realized, by the way, that my digitized pen, the little mark that it leaves when I hover over it, is not seen in the video, so I'm going to have to remember to use the mouse here to point. If only we had a built-in pointer in our computer system. So yeah, so then your column address then operates this mux, okay, that then selects a particular grouping of bits. Okay, so that's how an SRAM cell works, or an SRAM as a whole. And so as you can see, when you make the SRAM larger, okay, this bit array becomes larger, and so these word lines are longer. Okay, the word lines here are longer, and so they require a longer delay in uh, in access, because remember, longer lines have more parasitic capacitance and resistance, and that RC delay that comes from having a resistor and capacitor in series is what we end up with here. And so longer lines, whether it be the longer word lines and the longer bit lines, because remember, we try to make the memory array as square as possible because it optimizes that delay. It reduces that delay. The optimal delay is usually from a fairly square memory array, and that's because it reduces the word lines and the bit lines. Because what you have to do to access this array is your most significant bits of your address go through the row decoder, which that has a propagation delay, and then the row decoder lights up one of these word lines, and that selects a row of memory. Okay, and then that activates these pass gate transistors, which then allow the bit lines to be changed. Oh, and before that happens, while data is going through the row decoder, these bit lines are charged up to a middle value. So they're charged up to the middle of their range. And then when we light up one of these row lines, then these transistors here then modify the bit lines ever so slightly, and from their neutral middle position, and then the sense amp picks up on that. Well, then so you have delay going through the word line. So you have delay starting from the row decoder, going through the word line, going through these pass transistors, and then going down these bit lines through these sense amps, and then through your multiplexer at the bottom. Okay, which takes the column address, the least significant bits of your address, and then selects a line. So that's how delay, how data moves through the SRAM, and that's why larger memories are slower, because they have larger row and column decoders, which have an increased propagation delay. They have longer word lines and bit lines, and the sense amps have to be bigger, and all of that. Okay, and then just real quickly, a DRAM cell doesn't have the 2-bit lines. It just has one, and so it doesn't have a differential sense amp. Okay, and whoops. And it just has a trench capacitor, okay, like that, and we'll just run it to a single-ended amplifier, and it still has a row decoder that lights up one of these word lines, and see, just even in this drawing, I can pack more of these guys, right, which kind of shows what I'm trying to explain here. Okay. So we can pack more and more of these in here, and so we still have the row decoder. We still have we have a single bit line, and then we have these sense amps. Okay, they're single-ended though, and then we still have the multiplexer, which has the column decoder in it. Okay. Now, of course, what's unique about whoops, I left out I left out the capacitor here. Okay. What's unique about DRAM is that over time these, there's leakage out of these capacitors through the pass transistor, and then also just the capacitor leaks through the dielectric because they're not perfect, and so we have to do a continual refresh. And the other thing is what we do is we charge up the bit line to a mid value, and then we go ahead and enable the word line. And what it means is that then uh, energy is transferred from this capacitor to the bit line, okay, and so we actually destroy the contents when we read. So reads are destructive. So what we have to do is we have to actually read the entire row into a register. So we're going to have flip flops here, okay. And so what we're going to do is we're going to read the data. When we read it, we're going to latch it into the flip flop, and then we have to then write back. We have to then force a write back into that row. So after we read the contents from DRAM, we have to then write it back, and your DRAM controller handles all of that. Okay. And then of course we have to have a periodic refresh, which the periodic refresh just goes along and sequentially reads a row and writes it back. Okay. Okay, I just wanted to remind you, since we talked about this stuff early on in the semester, and then kind of jumped into pipelining and everything else, and so I wanted to just kind of refresh your memory of how that works. And so actually this would be a good quiz question. Draw a SRAM cell and a DRAM cell. Okay, that's your, what is it, third quiz question. I'm on the ball here with these quiz questions. Okay, so now that we're talking about memory hierarchy, I just wanted to review that material so you can kind of have a better visualization of how changing the size of the memory impacts its performance, and how changing the type of memory impacts its performance. Okay. All right. This is kind of a neat little graph that just shows how the density of DRAM has exponentially increased, the cost has exponentially decreased, and the access time has kind of more linearly increased, or decreased rather. Okay. Now, what's not shown in here is the bandwidth increase, and that would be really a nice thing to see here in this table. Is how the bandwidth has increased, because the bandwidth of these memories has increased quite a bit more than the access time. Because notice they say total access time to access a new row or column. Okay, so when we talk about latency, what ends up happening is you pay a pretty large penalty to access a piece of data in a row, and then once that you deliver that first piece of data, then you could just fire off the rest of the data in that row very quickly. So as you can see, then you end up with a lot more bandwidth. So you still have a high latency, but you have increased bandwidth. Okay, so that allows us to exploit spatial locality, because spatial locality says there's a good chance we're going to use data that's around the data that's being requested. So then that's where we get the bandwidth from. And if you think about how DRAM is constructed, okay, or even SRAM, you can see that how that works. Basically, you pay the huge penalty to take your address, chunk it up, go through the row decoder, okay, go and light up this row, and then of course, while you're doing that, you're charging up your bit line, and then sensing the bit line, and then storing it into these flip flops. Well, once you've paid that huge penalty, then the only penalty you have left is the time to go through this box. Okay, so actually, the column decoding, so to speak. So when you access the first piece of data in a row, okay, you now activated that row, which means it's the data in that row is stored in these flip-flops. Then accessing other data within that row is very fast because it's just going through this mux. Okay. So as a result, you want your cache systems to take advantage of that. And our simple instruction cache does that as well. When it has a cache miss, it refills the entire cache line. And we'll talk more about cache lines here shortly. But it takes advantage of what the memory that we fetch out of is called burst mode. And so you pay uh, a certain amount of time to access that first piece of data in the row, and then after that, it's like a tenth of the access time to access each remaining piece of data in that row. So burst mode it'll the cache lines are lined up with the rows of the memory, and so then accessing a cache line, it takes a few cycles to access the first word in that cache line, and then the rest of them to pull in the rest of the cache line is very fast. Okay. All right. I might be getting a little out of myself, so you may be struggling to keep up. That's the problem. When I get ahead of myself, I don't go in that natural progression that I've set up when I created these slides, which is supposed to slowly build the material up in your mind. But when I go ahead of myself, it kind of wrecks that. So I apologize for that. I just get so excited about this stuff. So, okay. Talking about a little bit more basics of caching. Caches are generally inclusive. We have inclusive and exclusive caches. Most caches that we talk about are inclusive, and really what that means is that um, all of the data that's in the level 1 is also in the level 2. And all of the data that's in the level 2 is also in the level 3. And all of the data in the level 3 is also in DRAM. Okay? That is what we mean by inclusive. Okay? And of course that works because the level 1 is much smaller than the level 2, which is much smaller than the level 3, and so on and so forth, right? So just if we remember typical sizes, the level 1 would be like we'd have 2 level 1 caches, instruction and data, and they're both 64 kilobytes in size, and then the level 2 is kind of around 256 kilobytes, and then the level 3 is in the megabytes, so it could be 512 kilobytes all the way up to 8 megs or something like that, or even higher on a server grade processor, and then memory, of course, is in the gigabytes. Okay. For now, we'll just assume a level 1 cache, and we'll actually start talking about how these caches work. So for now, just assume that we have a level 1, but keep in mind that we can very easily conceptualize that, use that concept of a level 1 cache to then create level 2 and beyond. It's just that the level 1 has different needs compared to the level 2, compared to the level 3, and we'll talk about those needs as we go along. For the level 1, its primary design goal is it needs to be fast. Because it runs at the speed of the processor, so it needs to be fast. And we actually will do things to improve its speed and over its miss rate. So we will sacrifice miss rate, so the miss rate may go up a little bit to maintain that higher performance. Okay. And we don't worry about the miss rate so much because we know we have a level 2, which reduces our miss penalty of the level 1. Okay. I'll talk more about that as time goes on. Let's just look at a simple direct mapped cache. Okay. I'll talk about what direct map means in a second here. Oh, real quickly, since I talked about inclusive caches, I want to talk about an exclusive cache. Once we talk a little bit more about how caching actually works, I can talk about a very popular exclusive cache that's used in all kinds of processors. It's called a victim cache. And in my 538 class, I actually have students read a paper on the original victim caching paper, where this concept was first discussed. And but anyway, when you pull in a cache line, you oftentimes have to replace the cache line that's already there. There's a cache line that's there, and this relates to placement, which we're going to talk about in a second here. And so you actually we use the term evict a cache line. And so the victim cache just simply stores evicted cache lines. And so by its natural definition, it is an exclusive cache, and it provides quite a performance benefit. So I'll circle back to victim caching after we've talked a little bit more about how um, level 1 inclusive caches work. Okay. All right, so the direct map cache is the simplest cache to design, simplest in hardware. Each memory location maps to only one entry in the cache, okay? And I've got a diagram that talks about this. So the lower address bits serve as the index into the cache, and then the upper address bits are used for the tag to uniquely identify a block, okay? Let's look at a diagram before we get too ahead of ourselves. Here we go. So for now, let's just assume there's only one level of cache, so this is actually main memory. Okay. And this is your level 1 cache. Okay. So here we have blocks of data, okay, inside our level 1 cache, and then we have in our main memory, we divide the main memory up into the same size of blocks. Okay. Now, because main memory is larger than our cache, okay, it requires more address space. Okay, so this is our actual address down here. Okay, I got to use the mouse pointer. This is our address here. And we take the lower bits of the address and we use that to index the cache. So this is our cache index. Okay, so let's see that is in fact what's happening here. Okay. Now this is a toy example where this is, I think it's only 4 times, the main memory is only 4 times the size of the level 1 cache. That's just a toy example. In real life, the difference between the cache and the main memory is going to be much larger. Okay. Um, okay. Although if you go from 64 kilobytes to 256, it's actually, let's see. Yeah, so that would be the level 2 is 4 times bigger than the level 1. Okay, let's look at these lower address bits. Okay, well, I'm supposed to be underlining. Hold on here. I'll draw it up here. It's not letting me go down that low. Okay, there we go. So we take the lower 3 bits, okay, and we use that to then index the cache here. Okay, and so there we see we have 101 and 101 here. And so any block that has the lower 3 bits of 101, okay, here we go, all these blue ones, map into this same block where the index is 101. Okay, so this is the simplest scheme because you can very quickly figure out where the data should be located in the cache. So when your processor presents the cache with an address, it takes the lower bits and uses that to index the cache, and then it goes and knows that because of these lower bits that particular block in memory that you're requesting has to live. If it is in the cache, it has to be in this one block. And again, we have this gray shaded one you can see where it has a 001 index, and so all of the blocks that have a lower 3 bits of 001 map into that same location. Okay, that is a direct mapped cache. And on the complete opposite end of the spectrum is a fully associative cache where data can go anywhere. So any of these blocks could map into any of these blocks in memory could map into any of the blocks in the level 1. So a fully associative cache doesn't actually have a cache index. Okay. So now the question you might be asking yourself is, well, how? Okay, so once you index the cache and you pull that data from the cache, okay, how do you then know that that's the exact data that you want? Because this is a many to one mapping here. Many blocks map to one block in the cache. So when you pull data from the cache, how do you know which one of these blue blocks, okay, it is? Whoops. Okay, how do you know that? Well, what you do is you store these upper bits in the cache. Okay, and that's our tag. The tag allows us to then identify which of these blocks it actually is. Okay, so you take the remaining bits after you've chopped off the index, and that becomes your tag. Okay, so now the way you tell whether a particular block is in the cache is you use the index, the lower address bits to index the cache. You then read the tag and compare it to the upper address bits of your address, and if they match, then you have what's called a hit, and your cache then delivers that data to the processor. Okay, and I think that covered this slide. Okay. So let's look at a simple hardware example. Okay. So for now, let's assume that a cache block is only 32 bits, i.e., one word. So if we have a 32-bit processor, then our cache block is only one word. Okay. And then let's say there are 1024 blocks in our cache. So we have 1024 words. Each word is 4 bytes, so this is a 4 kilobyte cache. Okay, which might be common for an embedded processor. Okay, the lower 2 bits of the address is the byte offset. Okay, we actually access memory a word at a time. Remember when we talked about the pipeline? We fed an address into our instruction cache, and out came a 32-bit word. And same in the data cache, we fed an address into our data memory, and out came a 32-bit word. So even though we can address bytes, even though the address is a byte address, we actually access the data at 32-bit chunks, so 4-byte words. So the lower 2 bits of the address we don't actually use. The cache doesn't use. The microprocessor uses it internally, but the cache doesn't. Okay, that's the byte offset. Okay, then now because we have 1024 cache blocks, that means we need, which is 2 to the 10. That means we need 10 bits for index. Okay, if we go back to this example, this simple example, we're using 3 bits to index, so that means there must be 8 blocks. Let's count. 1, 2, 3, 4, 5, 6, 7, 8. Yep. So 8 blocks means we need 3 bits of index. If we have 1024 blocks, we need 10 bits of index. Okay? And so then the remaining 20 bits that's left in the address is our tag to make up 32 bits. So again, the lower 2 bits aren't used for the cache because that's the byte offset that selects which byte within the 32-bit word. The microprocessor uses that internally, so don't worry about that. Then the next 10 bits is used to index the cache, and then the remaining 20 bits is the tag. So you add all that up and you get 32 bits. Okay, so what does that look like? Okay, this is what it looks like. Okay, so this is what a cache can look like. So here's our byte offset. Notice it doesn't even go into the cache. The microprocessor keeps track of it and uses it. The microprocessor uses it and it has to do shifting internally and stuff if you're doing like load byte or store byte, and there's alignment that has to go on, but we won't talk about that right now. I would like to spend a little bit of time in lecture towards the end of Chapter 5 talking about how byte access works in the microprocessor, but for now, don't worry about it. So that doesn't even go to the cache. Next 10 bits goes to the index, which allows us to then index our cache, and then the other 20 bits is then stored in as tag. So what we end up doing, though, is to access the cache, we take the 10 bits, we feed it in here, and that then allows us to pull the data and the tag from that cache block. This is a cache block right here, our cache line. We call them cache line or cache block. We use that term synonymously. Okay. Then what do? Well, we take the tag from our address and we compare it to the tag that we just read from this block. And if they equal, then we have a hit. Well, not quite. We have to have this valid bit. We have to keep a single bit inside the cache that indicates whether this particular cache block is valid. Because it could be when the cache starts up cold, it has randomized data, so it could be that the data in here is actually garbage, and we could inadvertently match to that data, and then we deliver garbage data to the processor. So when a cache is first started up, all of the valid bits are cleared to 0, and then as we bring data in, we set those valid bits to 1. And then as we talk about with cache coherency and some other things, there are some other things that may happen while the processor is running that causes cache lines to be invalidated. So the way we invalidate a cache line is we just set that valid bit to 0. Okay? So again, to access the cache, we pull the 10 bits of index. Okay, use that to grab the piece of the piece of data, the block, and then we compare from that block. We compare the tag, and we look at the valid bit. And if the tags compare and the valid bit is set, we then identify this as a hit to the microprocessor, and then it will then grab this data and use it. Okay, if we find that the data is invalid, which is either because the valid bit is if there's a cache miss, which means that either the valid bit was not set or the tag didn't compare, then we have what's called a miss. The microprocessor will stall and wait for the data, and the cache controller will then go out and retrieve the data. Oh wow, we are quite a bit out of time. So let's see here. Okay, I think this is a good stopping point. Where we'll pick up next time is we will go ahead and expand our cache to have actually multiple words within a block, which is a more realistic design. And this is actually the design of a real processor. Okay, so there was a real processor that was designed probably in the 80s or 90s that had a 4 kilobyte data cache, and this is what we're looking at here. Okay, so we'll pick back up next time and by expanding this cache to have multiple words within a block, which is a real example. We don't you don't have a cache. There's no cache that has a word per block because you're not exploiting spatial locality, right? You're only exploiting temporal locality at that point. Okay. All right. Well, if you have any questions, do post your questions to the lecture discussion board. No one's really used that, so please ask questions. Okay, real quickly, it occurred to me as I was editing the video that I forgot to give you another quiz question at the end. So here it is. I want you to define a cache hit and a cache miss. Okay, that's your quiz question. All right. With that, I hope you all have a wonderful day and stay healthy and happy.